In this video, which is sure to be nominated for an Academy Award at the end of the year, we'll be exploring the third of our conic sections, which have been increasing in complexity. This time we'll be talking about ellipses. With ellipses and eventually hyperbolas, the terminology of the different aspects of the graphs and the shapes are much more important. Please refer to your class notes for the identification of all of these different parts of an ellipse, including the center, the foci, the vertices, and the difference between the major and minor axes. As we discuss these, it's very important that you're able to correctly identify these parts of both an ellipse as well as the corresponding parts when we discuss hyperbolas next time. Recall that the standard form for our ellipse equations appears to be very similar to that of our circles. There's a good reason for that, because a circle is simply a special case of an ellipse, just like a square is a special case of a rectangle. Now, we do have separate forms for horizontal and vertical. That's how your book presents it. But I think it's actually more helpful just to think of one simple equation for ellipses and then to think of the a value as the x radius, the distance that you're going to move horizontally from the center to find the edges of the ellipse, and think of this value as the y radius, the distance that you'll travel vertically to go from the center of the ellipse to its edges. The direction of the ellipse is then determined by which one of these is larger. If the y radius is larger than the x radius, then the ellipse will be oriented vertically rather than horizontally. If we think of ellipses this way in terms of x radius and y radius, sometimes this last part, finding the distance to the focus, can become a little bit confusing, because you may assume that the x radius is always a and the y radius is always b. Not so. Instead, the foci are always oriented to the same direction as the ellipse. And so the a value here is always going to be the longer of the two radii. Just something to remember. I think it simplifies things to think of these as the x radius and the y radius, but just remember that when you're trying to find the focus, you're always going to use a squared minus b squared, where a is the longer of the two radii. So now let's get into an example. Just like we did with the previous two examples, we want to look at why this is the equation of an ellipse. Before we even get started, we know that this is going to be an ellipse. Like the circles, we notice that there are two quadratic terms, one for both x and y. That narrows things down a little bit, indicates that this is going to be at least either a circle or an ellipse at this point. The reason why we know this is going to be an ellipse is that the coefficients in front of these two quadratic terms are not equal. That will lead to differentiating radii in the x and y directions. Right now, I'm not sure which direction this ellipse is going to be going, but I am going to just take a look at this standard form on the right-hand side and recall we want to take our initial equation and move it into that standard form. Just like with circles and parabolas, the first step is always going to be to group our like terms. 9x squared minus 36x plus 4y squared minus 24y equals negative 36. I got that constant over to the other side. Now we need to begin the process of completing the square. What makes ellipses and eventually hyperbolas a little more difficult is because they do have these coefficients in front that are going to be different. And so we need to take that into account whenever we are completing the square. It's always best to remove any common factors that you have to make completing the square much easier. So from the x terms, I'm going to remove the 9 and leave x squared minus 4x and leave a blank for what the value to create a trinomial square, and take out the common factor of 4 from our y terms. And just like we did before, I'm going to leave some blanks, one on top of the other, for the values that we're going to add to the right-hand side to offset the addition that we do to the left-hand side. Now going back and looking at those x terms, what value would create a trinomial square? I hope we're getting comfortable with this at this point. It should be the value of 4. Now, remember, I didn't add 4 to the left side. I added 9 times 4 to the left-hand side. That's 36. So I need to remember to add 36 to the right-hand side as well. Now looking at the y terms, we need a 9 to create a trinomial square, and again, 4 times 9 is what I actually added. So that ends up being 36 again. So we add 2 36s to the right-hand side, and now let's continue to simplify by factoring. 9 times the quantity x minus 2 squared plus 4 times the quantity y minus 3 squared, and when we add up all of that on the right-hand side, we end up with 36. Nice perfect square. You're going to see that quite a bit. Now remember that our standard form has 1 on the right-hand side. So in order to get that, we are going to divide both sides of the equation by 36. When I divide the left-hand side, please note that it does apply to both of those sets of terms, and we get some cancellation going on. 9 divided by 36 is the same as 1/4, so that's going to be x minus 2 quantity squared divided by 4, plus y minus 3 squared divided by 9, and that all equals 1 now. So what we've just found is an ellipse with a center at the point 2, 3. The x radius is going to be 2. The y radius is going to be 3. So that means this is going to be a vertical ellipse. So let's go ahead and graph this ellipse. I'm going to place my center at 2, positive 3, again with that open dot indicating that the center is actually not a point on the ellipse, not a solution of the equation. The x radius is going to be 2 units, and so I'm going to plot 2 points that are 2 units left and right of the center. The y radius is 3, so I'm going to plot points to the north and to the south that are 3 units from our center, and then I'm going to connect them with as smooth a curve as possible. Let's also find the focal radius so that we can plot the 2 foci that were used to construct this particular shape. We'll also identify the eccentricity of the ellipse. Remember that when using the c squared equals a squared minus b squared formula to find the focal radius, that's c, a is always going to be the larger of the 2 radii, b is going to be the smaller. In this case, the larger is the y radius, the major axis is going vertically, and that radius is 3, so a squared will be 9. The minor axis has a length of 4 going across. That means the minor radius is 2 units, so 2 squared is 4. That means that c squared is equal to 5. C is equal to the square root of 5. That means our 2 foci are going to be a little bit more than 2 units, both above and below our center point. They're going to be exactly the square root of 5 units away, and so we can actually write the coordinates of that. Since our center point is at the point 2, 3, our 2 foci, again, are going above and below. That means the y variable is changing. So the foci have coordinates 2, 3, plus and minus the square root of 5. Those are the coordinates of the 2 foci. Recall that we also have this idea of eccentricity. That's the relative roundness of the ellipse. That's always the focal radius divided by the semi-major axis. In this case, that's the square root of 5 divided by 3. That's roughly equal to 0.75. So this is much more like an oval than a circle. Just like we did with our circles and parabolas, we're now going to look at an example where we write the standard form equation of an ellipse based upon information about it. And just like before, plotting the actual graph is the best way to begin. So I'm going to start by plotting the two vertices, one at 1, 3, and one at 9, 3. Before I go and start using this minor axis length of 6, though, I want to find out what the center point is. With vertices at 1, 3 and 9, 3, the major axis has a length of 8 going across. That means the center is going to be 4 units from each of those points, smack in the middle. That means our center is going to be at the point 5, 3. Same vertical distance from the x-axis, but halfway between x equals 1 and x equals 9. Now we can plot the vertical radius by using this minor axis length of 6. Remember, the minor axis goes across the entire ellipse, so the vertical radius, the y radius, is 3 units. 3 units above and 3 units below the center, and connect all of these 4 dots with a smooth curve. This gives us plenty of information to write the standard form equation of the ellipse. I'm going to put together the building blocks of it here. The two quantities squared, one with x and one with y. Both are going to be divided by their corresponding radii, and all of this should equal 1. So now I start filling in this information. This should be the quantity x minus 5 squared, and the other one should be y minus 3 squared. And remember, what's going to go underneath of each of these quantities squared will be the corresponding radius. So the x radius of 4 units will be squared underneath of x minus 5 squared, and the y radius of 3 squared is 9, will fall underneath of the y minus 3 squared. Now we've written the standard form equation of the ellipse with vertices at 1, 3 and 9, 3 with a minor axis length of 6. You can be given lots of different information about an ellipse to be able to write the equation, including the eccentricity, the coordinates of the foci, and so you'll just have to adjust in each situation and use the graph to help you write the equation of the ellipse in standard form.